Hi, everybody. This video is on section 5.2 of the book. There's a little confusion on it, so I definitely want to cover it. So let's take a look at some of the slides. Definitely not going to cover it all, but I'll look at some of the slides that I have on 5.2. So first, sigma notation means the sum. This is summation. This symbol here is summation. I'm hoping everybody knows that. I think we used that in the later parts of algebra. What that means is this, and it looks a little weird here, but it's the summation where I equals 1 to 6. So we start I at 1, then we go to 2, 3, 4, 5, 6. And here is I. So what it says, first put a number 1 into that function, and if I put a 1 in there, I just get 1. Then add it, start with I2, put a 2 in there. Start with I3, 4, 5, and then 6. And then add it up, 11, 18, 19, 20, and you get 21. This next one, it says we're going to start I at 3. So first we put a 3 and square it. Then we add and put a 4 and square it, the next I number. 5 squared, 6 squared, and 7 squared, and we stop because this is the stop number, stop at 7. And then we find that answer. Go ahead, you can find it. Here we're putting a 0 through 5. So first you put a 0 into here. 1 plus 0 is 0. Then you put a 1 in there. 1 plus 1 is 2. First you put a 0 in there, I'm sorry, and 1 plus 0 is 1. We put a 1 in there. 1 plus 1 is 2, 3, 4, and then you put a 5 in there. 5 plus 1 is 6, and then you add all these up. So that's just a summation. That was very quick. I'm hoping you all know that already. I'm going to put this in my calculator and show you how to do this on the calculator. So let's do the first one on a calculator. Give me a second. There's got to be an easier way to make this big. I know there's a format page on here somewhere. Oh, I just made it disappear. Let me do this. I was hoping I can make it bigger so we can see on the calculator. So on the calculator, to do a summation problem, what you have to do is click on Math, and then scroll all the way down to number 10. And I'm using the TI 84 Plus, just like I said at the very beginning of class. This is how we're going to go. And do you see it says summation? And when you hit enter, the summation pops up. Now it says I equals 1 to 6. I'm not using I. I'm just using the X button on here. It doesn't matter what variable you use. I'm using X. And then I'm going to put 1, and I'm going to arrow up to 6. And this function says it's going to be I, which is the variable X. And then now when I hit enter, do you see it gives me 21? So it does the math for me. This is good on the parts of the test where you don't have to show your work. You can plug it straight in. So let's do the next one because we didn't add up that square, I square. So I'm going to math, number 10, summation, and I'm going I or X equals, it says 3 to 7. And in the function, I'm putting I square, X squared. And when I hit enter, so if you would have did 3 square was 9, 4 square is 16, 5 square is 25, 36, and then 49, and add them all up, you would have got 135. So the calculator does a summation for you kind of quick if you don't have to show your work. If you have to show your work, then you do it the way I did it up here and then add them all together. Okay? Just wanted to make sure We know that summation. All right, let's go to the next slide. All right, let's see what we got next. Okay, so theorem 5.2. Theorem 5.2 summation formulas. You have to write down all four of these. You're going to need them on the test. Write these down. If I can find them now, what happened? I clicked on something wrong. There, it should be here. Write these down. This is theorem 5.2. Change in summation formulas to non-summation formulas. Do you remember that I that we just did? That was number 2, problem 2. The summation of from 1 to, what do we do? Let me go back. We did summation from 1 to 6, okay? So we did the summation of 1 to 6. You can change that. This is n, by the way. So just by putting a 6 in here, this is 6 times 7. 6 plus 1 is 7, is 42. 42 divided by 2 is 21. Do you see? This is the abbreviated version of the summation. It's kind of like the algebra way of doing the problems. You're not doing summation anymore. You're changing it. They prove that this equals this. So you have to have these written down. For I squared changes to this problem. I to the third changes to this problem. That last problem was from 3 to 7. You cannot use this for that last problem because this only works when I starts at 1. So I can't do that problem using this method for summation because it only starts for I equals 1. But let's do it for I squared. Oh, that was the I squared. It was from 3 to 7. We can't do that one. All right. So we got to write these down because we're going to use these theorem 5.2 at least 3 times on this test. The show your work part of the test, part B of this test. All right, so let's go to the next slide. And this problem says evaluate this summation here. I equals 1 to n, and we have n squared I. So I show you all the work here, but I just want to show you what the process is. First, you want to try to factor out any n's that you can. Factor out n's. And if you notice, see this n square? I'm going to just factor it out. That's what they did. This is 1 over n squared, and they factored out the 1 over n squared. And when you factor that 1 over n squared out, you're left with the summation of I plus 1. And there's a sum, and summation property says if you have the summation of I plus 1, you actually have the summation of I plus the summation of 1. You can separate those. Okay. So now the summation of I. Do you see this? Go back one slide. The summation of I from 1 to n changes to n times n plus 1 divided by 2. That's how this summation of I changes to n plus 1 divided by 2. Now, here's a constant. This is a constant. So let's go back to the formulas. If you have a constant, any whole number that is not a variable, you have to do the constant times n. So this summation changes to n, even though that doesn't say it. The constant, or what's the constant? Oh, the constant is 1. I'm sorry. Boy, let me clear that. Give me a second. So this changes to 1 times n. And by the way, 1 times n is just n. That's how they got that. You see the constant times n. The constant is 1. 1 times n is n. So from here, we just do algebra. We on the top, if I distribute, I got 1 over n squared plus n over 2 plus n. This is the problem. I'm going to put n over 1. 1 over n squared. Then I'm going to multiply this by 2 over 2 so the denominators are the same. So on top, I've n squared plus n plus 2n. On the bottom, I just have 2. This changes to 3n, so I have 1 over n squared times n squared plus 3n all over 2. And if you look at, I can factor out another n here. So I have 1 over n squared, and then I just factored out an n, and I get n plus 3 over 2. One of the n's cancel. So I end up with, now if I multiply this, everything by 1 over n, I just bring this n over there, multiply it, I get n plus 3 over 2n. So that's just evaluating. And at some point later on, we're going to change n's to infinity and find out what this all equals. Yeah, we'll worry about that later on. So evaluate these i's. You can change them to n's using 5.2. You can change them to n's using theorem 5.2. Okay, so this is a tough problem for many people. It's not easy. So let me show you, let me go through, I'm going to try to go through this. I don't know if I have enough room here, and I don't know what I just clicked. Oh, Lord, what just happened? Okay, it's somewhere over here. So this is where we're at. So let's draw this picture first. It says approximate the area of the region of the x-axis between 0 and 2 using right endpoints and 5 rectangles. So here is my graph, and it's negative x squared plus 5. So here's 5, and negative x squared looks like this graph here. So this is our graph. Let me draw it a little bit bigger or a little bit better. I don't know if I can do that. So here's 5. I'm going to try to be a little neater. There we go. And it says I want to approximate the area between 0 and 2, x between 0 and 2. So we actually want to find the area of this region. We want to find the area of this region. I'm putting dots in between 0 and 2. And it says use 5 rectangles and use the right endpoints. So I need to separate this into 5 sections. 1, 2, 3, 4, 5. In other words, at each of these, this is a rectangle, and then you come up. I'm going straight up till I hit the graph and come over. Straight up and hit the graph and come over. Straight up, hit the graph and come over. If you look, straight up, hit the graph and come over. If you look, I have 5 rectangles. This last one's kind of small. I don't think I drew it exactly right. Oh, by the way, can you tell me why I didn't draw it right? The x-axis should be at the square root of 5, this m, which is over here. So it actually has me come up and come over there. Do you see this? The x-axis should be negative 5, negative square root of 5 and positive square root of 5. 5 is like 2 point something. So when I get a 2, I go between 0 and 2. We're not doing all of that area. Okay, so I still have to set up this function now. If you look, to find the area of these triangles, and that's what we're trying to do, find the area of 5 triangles, this is the width. So the area of a triangle is length times width. So our width is between 0 and 2, and we're going to divide it into 5 triangles. So there should be 5 widths on here. Give me 1 second. I'm just trying to hit pause. So my question is, how far is, I did it again. How far is each width? Each width should be the same. Do you see, we're dividing from 0 to 2. That means there's 2 units that we're dividing by 5. Do you see this first width is at 2/5? The second width, 2/5 plus 2/5 is 4/5, 6/5, 8/5, and then 10/5, which is 2. You see, so the total width that we're going to find the area is 2, and we're going to divide it into 5 rectangles. So when we do our function, by the way, we're going to do a summation here. And we're going to do the summation of the length of this rectangle times the width. Well, the width is 2/5. The width of this rectangle is 2/5. And now we have to find the length of the rectangle. And there's going to be 5 rectangles, by the way. So we're going to add up 5 rectangles from 1 to 5. So I need to find how high these, do you see at each point, how high does this rectangle go? How high does this rectangle go? How high does this rectangle go? And I know the x value for each of those rectangles. The x value is 2/5, 4/5, 6/5, 8/5, 10/5. So if I plug the x value into the function, I'll know the y value. So that's what we're going to do. We're going to plug in 2/5 for the first function and find the length. But how do I do the second 4/5? So it's 2/5 times I. Do you see? 1 is 2/5 times I. If I equals 1, then I get 2/5, this spot here. If I equals 2, I get 4/5, this spot here. If I equals 3, then it's the third rectangle, 6/5, and so on and so on. So here's my function. Once again, I'm writing my function from I equals 1 to 5, and I'm going to put 2/5 I into the function times the width, which is 2/5. Now I'm actually going to put 2/5 I into the actual function. So I do a summation of I equals 1 to 5, and I'm putting, here's my function now, negative x squared plus 5, and everywhere there's an x, I'm putting 2/5 I. That's it. I guess I could try to write that a little neater. Summation of I equals 1 to 5, and it's negative x squared, and x is 2/5 I, plus 5. This is the function. And then at the end, I'm going to multiply it by the width, 2/5. This is the length. This is how high it goes, and this is the width. So this is my function. All I have to do now is plug this into my calculator. So you have to be able to plug this into your calculator correctly, okay? And by the way, this is finding the area using the right endpoints. There's definitely a question on this. I think there's a question on this on part A and part B of the test. So let's, or at least part A. So let's see if we go to math and go down to number 10. And our function is x equals from 1 to 5. My summation is, by the way, my summation, and this is kind of important, is going to be the whole thing. You have to this is the whole summation that we're doing. So there's extra parentheses. You need the big summation formula that your calculator gives you already, but then you need a parentheses and type in negative parentheses 2x divided by 5, close parentheses and square it, and then plus 5. And I'm going to close the function parentheses and then do a parentheses 2 divided by 5, close that parentheses. It's a little bit of a mess. Let me show you how I type. Oh, let me hit enter first to make sure I'm typing it in correctly. And then I think we had the final parentheses closed, and I get 6.48. When I put this in my calculator, if you don't get 6.48, you're typing it in wrong, because this is what the book tells me the answer is also. 6.48. So let me type that in for you again to show you how I was. I don't know if that's even wise. I really wish I had one of those other calculators that do online, and camera that's not hard to focus. Okay, so I'm going to math and then scroll down to number 10, summation, and it's I from 1 to 5. I'm using X, 5 rectangles. And so the first, this is my summation parentheses, but I need a function parentheses now. Oh, wait. I typed in the wrong thing. Sorry. Now I need a summation, a function parentheses. So I'm starting my function parentheses, negative parentheses 2 divided 2 times X divided by 5, plus, we got to square it, plus 5. See, my function is done, so I'm closing my function parentheses, then opening my width parentheses now. That was my length. Now I'm doing my width, 2 divided by 5, closing that parentheses. And if I move over once, that's my summation formula parentheses still there. And when I hit enter, you should get 6.48. Okay? So that's using the right endpoints. You see, if on a rectangle up here, this is a rectangle. We use the right endpoints to find the height. What happens if we use the left endpoint? So let me show you. By the way, on the test, they're going to ask you to do both ways, use the right endpoint and the left endpoint. So I'm going to the next slide because it says, hey, now do the left endpoint. So here, let me draw the graph again. This goes to the square root of 5. And if you look, here's a graph. It goes from 5. Oh, sorry, I drew it wrong again. So this goes down here and down here. This is the square root of 5, but this is 2. And there are 5 rectangles. 1, 2, 3, 4, 5. Last time we used the right endpoints. This time we're going to use the left endpoints. I'm drawing the left endpoints. In other words, the left side we're doing here, and we're going outside of the line in this case. We're using the left side to draw in the previous, we used the right side, and we went inside, the right side to go inside. But now we're using the left side to go straight out. So these are the left endpoint rectangles. The width is still 2/5, right? Each width is still 2/5. It's too long, and there's 5 rectangles. The height, though, we're going to start here at 0. Do you see at the 0 point? And then we're going to go to the next height will be at 2/5. 4/5, 6/5, 8/5, and there won't be a height at the 10 because we're going to we're doing the left endpoints. So when we do the function, when we do the summation of I equals 1 to 5, we got the length and we got the width. The width is still going to be 2/5. However, the function is going to be different. The function, you put the width in there, and last time we put I. But we can't put I because if you put a 1 in there now, you start at 2/5. We have to start at 0. So we're putting I minus 1. I minus 1, do you see if I put a 1 in the I now, 1 minus 1 is 0. 0 times 2/5 is 0. And it tells me how high the graph is when I put 1 into this function now, since it's I minus 1. So this is what the function looks like. 2 times I minus 1 over 5. This is what the function looks like because we're starting at 1. Now, if I put 1 in there, we're doing the left endpoints. That turns to 0. When I put 2 in there, that turns to 2 minus 1 is 1. We're looking at the second rectangle now, 2/5, the third rectangle, the fourth rectangle. So this is the function I'm typing in. So I'm putting 2/5 I minus 1. So I'm going to do the summation again from I equals 1 to 5. And I'm going to put this into my function, negative x squared plus 5. And in the x, I'm putting 2 times I plus 1 over 5. This is my function, parentheses. And then I have a parentheses for the width. And don't forget, I have one big parentheses for the whole summation. Now, if you put this into your calculator, I'm just going to give you the answer, and the answer is 8.08. Do you see the first one was 6 point something because we didn't use all of, there was gaps missing. This one is more, 8.08. Because the rectangles fall outside. When you use the left endpoint in this case, the rectangles fall outside. So the area is more than what it actually is. If we use the right endpoints, the area is less than what we have. So our area should be, our true area should be somewhere between 6.48 and 8.08. Our true area should, and it doesn't necessarily fall right in the middle, but it should fall somewhere between here. I'm going to do the true area on our calculator, how to do a true integration on a calculator in case you haven't done it. Now, there's a couple ways of doing it. I like using the graphing method when I do this. So I'm going to first graph our function. I go to y equals, and I'm typing in our function, negative x squared plus 5. There's our function. Now, when I look at my graph, I don't have the right window, so I'm going to change the window. Negative 10, 10, negative 10, 10. So when I look at my graph, there's my graph. And I want to know the area between 0 and 2. Do you see how the line passes on to the right of 2? That's the square root of 5, the x-intercept. So to now, first you put it in y equals, you graph it. Now you hit a second calculate and go down to number 7. Second calculate and go down to number 7. It says integrate. Where are you integrating? I'm integrating. The lower limit is 0 and my upper limit is 2. And do you see it shades in the spot that you're integrating? It says what's the area? And the true area is 7.333. In other words, 7 1/3. So the true area is 7.333 or 7 1/3. You see it's somewhere between these two. Kind of cool, huh? So the area was too small because the rectangles were inscribed, and then the other one, the rectangles were outside of the actual, so the area was too much. The true area is the entire, what was truly shaded, and our calculator showed us that. All right. And that's all I wanted. I mean, you can look, if you want to look at these slides, don't forget these are on the bottom of your module. They go through the same process again. Wait, this is a little different. It was find the upper and lower sums. Okay, so this is a little different process if we're not using our calculator. So let's go. Let me go through this process. Give me a second. Okay, so this is the same thing, but this is a different process. This is called using the limit process. And there's two questions on the show your work part of the test here. So the limit process or the limit definition. Limit definition. And look at these problems on the reviews that I put also. Limit process or the limit definition. So here's x squared, and here's our graph for x squared. And we want to find the area between 0 and 2. Here's 2, here's 0, and we're looking for this area here. You see, it's always the graph and the x-axis. So this is x squared, and we want to find that area. The question is, what is our width? And how many rectangles? They don't say how many rectangles do we need. So our width is still 2, and we're going to divide it by the number of rectangles we use. I could use 5 rectangles. I can use 100 rectangles. Or I can use an infinite amount of rectangles. Would you agree that the more rectangles you get, the more accurate your answer is? Do you see the less gap that's outside of the graph or inside of the graph? If you use more rectangles, the answer gets closer and closer to the true value. And then eventually, if I use an infinite amount of rectangles, I get the true area. So the width of this, how wide we're doing each rectangle, is 2 divided by the number of rectangles. We don't know how many rectangles. I'm just putting 2 divided by the number of rectangles. There's our width right here. Our length for the right endpoint is always going to be the width times I, right? Because we start at 1. There's our first one, a second width, third width, fourth width, and we can have an infinite amount of widths. So this is the same thing we did for our right endpoints last time. And now what did I do with this function? I put this into the x value. Here's the function. I'm just putting 2i over n into the x squared. That's what we did here. Now at this point, do you see, we don't know what n equals. We don't know how many rectangles we're using. So we can't put this into our calculator. So what do we do? Well, I'm going to factor out these two n's, which is an, by the way, this becomes, 2i squared changes to 4i squared if I square both. And if I square this n, it becomes n squared times 2 over n. So if you look, I have 3 n squares. We're going to take out the n squares. We took out the n squares, and I have a 2 times 4, which is 8 I took out. And I'm just left with an I square in my summation. So I can take out constants and n's out of my summation because n is a set number. It depends on how many rectangles we want. If I put 5 rectangles, I'm going to say n is 5. If I want an infinite amount of rectangles, I'm going to say n is infinity. So now I'm going to go to my 5.2 and change this all to n's, right? The summation of ni plus 1. If I go back to I squared, look at 5.2, if I can get to it. Oh boy, 5.2 says I squared is changed to this. The summation of I squared changes to that. So you better have those summations written down. Do you see the summation? Uh, this, here we go. This I squared changed to that. We got that right off of 5.2. And then there's just a lot of algebra involved in multiplying. This is what we get. I'm going to I'm going to multiply everything by 4, the top by 4, 8, 12, and 8. What I end up with is 8n3 plus 12n squared plus 4n. And then I'm still going to divide each by 3n squared on the bottom, this 3n squared. 3n squared, 3n squared. N squared and n cancel, so I have 8 n3, not n. I'm multiplying it by n3. I'm sorry, n3, n3. These n3s cancel, and I have 8/3. I have one extra n on the bottom. 12 divided by 3 is 4, and then here I have 2 extra n's on the bottom. Now this is my answer, and I have to say how many rectangles am I going to use? I want to use an infinite amount of rectangles, so everywhere there's an n, I put an infinity. 4 divided by infinity is 0, and 4, once again, 3 times infinity squared is still infinity, so 4 divided by 0 is infinity. So my answer to this problem is 8/3. That's the actual answer, 8/3, 8.08. I think that's that's not 8.08, that's not right. So the answer is 8/3. And you get the same answer if you use the left endpoints. Do you see, once again, the left endpoints you have to use, because you're going to start at 0 in this case. You start at 0, you have to use the I-1 to get a 0 when you put a 1 in there. And you go through the same process. It's a little different, but you still end up with 8/3. I mean, this is a little bit more algebra because you have to square that. I'm not going to show you all that algebra, but you have to FOIL that and square it and then combine the terms, and this is what you end up with. And plugging in I square here, plugging in the I right here, remember I from 5.2, and the constant has an n also. Don't forget there's a constant n. The summation of a constant equals, that's a constant, equals constant times n, 1 times n. And then when you set everything, when you multiply this back, these turn to 0, and you still get 8/3 as an answer. Doesn't matter if you use right endpoints or left endpoints. When you use an infinite amount of rectangles, you get the actual answer, and the actual answer is 8/3. So that's pretty much, I think, 5 point, and take a look at theorem 5.3. That's a limit definition. Finding the sum when you're setting n to an infinite amount of rectangles. So that's called the limit definition or the limit process. So just remember those words when you read the other point. And there's an x3. I'm not going to go through the algebra there. There's a lot of algebra there. But you can take a look at the same process. You find the width. You see you're going between 0 and 1. So each rectangle is 1 divided by the number of rectangles you have, the width, because there's only the distance between 0 and 1 is only 1. So it's 1 divided by n, and you do the same thing. You plug that into the function. And unfortunately, the function is to the 3rd power. And then when you change I to the 3rd, you get this crazy thing. And then you have to go through the whole process again. The rest is algebra. All right, so that is 5.2. I hope that it helped. That is a tricky section, and you really have to practice those. You have to write down 5.2 because there are 3 questions you need those 5 on the show your work part of the test. The limit process, the limit definition, and using 5.2 summation. So all 3 of those problems, you're going to be using 5.2 to change the I's to N's. You guys, let me know if you have any questions.